All right, let's just jump right in. We're about to get into one of the weirdest, but also one of the most powerful ideas in all of modern physics. And what's so cool is that it all starts with a simple, everyday saying, but it points to this absolutely bizarre quantum truth that's hiding just beneath the surface.
You've heard that saying, right? A watched pot never boils. You know, it's something we say when we're getting impatient. But what if I told you it wasn't just a saying? What if there was a real physical principle at play, where the very act of looking at something, observing it, could literally stop it from changing? Well, in our everyday world, yeah, it's just a saying. But down in the quantum realm, it's a fundamental, mind-bending reality.
And that's exactly what this is. It's called the Quantum Zeno Effect. And it's this incredible, startling demonstration that in the world of quantum mechanics, you can't just be a passive bystander. The very act of measuring something is a physical interaction that doesn't just observe the system's destiny, it can completely change it. It can literally freeze it solid in time.
So to really wrap our heads around this, we've got to look at where this idea even came from. And you might be surprised to learn it didn't start in some high-tech lab. Nope, the story actually begins way, way back in ancient Greece.
So the name, Zeno, comes from Zeno's arrow paradox. It's a classic. Zeno basically said, hey, think about an arrow flying through the air. If you look at it at any single frozen instant in time, it's not moving, right? It's just there. So his question was, if time is just a bunch of these still moments strung together, how is motion even possible? Now, okay, calculus eventually sorted out that philosophical brain teaser. But fast forward to 1977, and a couple of physicists realized that in the quantum world, this idea isn't just a puzzle, it has real physical teeth. They worked out the math and showed that if you could somehow measure a quantum system continuously, you would actually literally freeze it in place, just like Zeno's arrow.
Okay, so how on earth does that actually work? How can looking at something freeze it? Well, the key is remembering that in quantum mechanics, observation isn't passive. It's not like just taking a picture. It's a full-on physical process that interrupts and, yeah, can even redirect the course of reality.
Let's picture an unstable particle, okay? If you just leave it alone, it starts to evolve into this fuzzy quantum state, a superposition, where it's both decayed and undecayed at the same time. But if we jump in and measure it really, really fast, basically asking it, hey, have you decayed yet? We force it to make a choice. And if the answer comes back, nope, still here, that whole fuzzy superposition just collapses. Poof! The particle is forced right back into its pure, undecayed state. It's like we just slammed the reset button on its decay clock. And if you do this over and over and over again, really fast, you never give it the chance to get anywhere. You've frozen it.
But why is that reset so powerful? I mean, why does it work so well? It all comes down to a really weird quirk in the math of quantum mechanics. You see, we tend to think of something decaying as this steady exponential curve, right? But it turns out for these infinitesimally short moments, right at the very beginning, the probability of the system changing doesn't grow linearly with time. It grows with time squared. That t-square behavior is the secret sauce. It means that right at the start, the change is happening insanely slowly. So by repeatedly measuring inside that tiny, tiny window, we're basically trapping the system in a state where its evolution has barely even started. It's a total hack.
Now I know what you're thinking. This all sounds like some wild, abstract theory cooked up on a blackboard. But how in the world could you ever prove something this bizarre is actually real? Well, the answer came from this absolutely brilliant and clever experiment back in 1990 over at NIST, the National Institute of Standards and Technology.
So here was the huge challenge they were facing. The theory says that measuring the atom will freeze it. But wait a minute, doesn't the act of measuring it, like hitting it with a laser or something, also mess with it? How could they possibly tell the difference between the Zeno freezing they were looking for and just, breaking the whole setup with their measurement?
And their solution was just genius. Pure genius. So here's what they did. They used a radio frequency pulse to try and nudge these beryllium ions from what we'll call state 1 over to state 2. Now to measure them, they fired a UV laser at them. But here's the clever part. That laser would only light up an ion if it was in state 2. If the ion was still in state 1, nothing happened. It just stayed dark. And that was a massive insight. They realized that not seeing light, the fact that the ion stayed dark, was a perfect measurement in itself. It told them, yep, the ion is still in state 1. And that very act of knowing collapsed it back to that state, all without ever having to physically blast it with a photon. It's a measurement by absence. Just incredible.
Okay, so we've got the rule down, right? Watching something freezes it. Simple.
Well, not so fast. Just when you think you figured out a rule in quantum mechanics, it loves to throw you a curveball. Because it turns out, sometimes, watching something can have the exact opposite effect.
And yep, you guessed it, this is called the Quantum Zeno Effect. In this case, a watched pot actually boils faster. Now, this isn't some crazy contradiction. What it reveals is something deeper. That measurement is always a physical interaction, and that interaction can go one of two ways. It can either cut the system off from its environment, which gives you the Zeno freezing effect, or it can actually strengthen its connection to the environment, which speeds up its change.
Here's a good way to think about it. Imagine a system is already perfectly tuned to decay into its environment. The measurements will actually mess up that tuning. They'll detune it, and that slows everything down. That's the Zeno effect. But what if the system is out of tune with its environment to begin with? Well, in that case, the noise from your measurement can actually help it find a way to decay, sort of broadening its options and helping it connect. And that speeds things up. That's the anti-Zeno effect. So you see, they're really just two sides of the same coin. It all just depends on the timing of your measurements and how the system is relating to its environment.
All right, so this is all super interesting, but you might be wondering, why does any of this matter outside of a physics lab? And that is a great question, because this is the part of the story where we pivot from a weird paradox to an absolutely critical engineering tool, and it's a tool for one of the most revolutionary technologies on the entire planet.
I'm talking about quantum computers. See, the number one enemy, the biggest challenge by far in building a useful quantum computer is something called decoherence. The qubits, those are the fundamental building blocks, are just unbelievably fragile. Any little stray interaction with the outside world, a tiny vibration, a random photon bumping into it, can completely wreck their delicate quantum state and introduce a ton of errors.
And this is where the Quantum Zeno Effect comes in like a superhero. It's a total game changer. By constantly and very, very carefully measuring a qubit, just to check if it's still in the right state, we can use the Zeno effect to basically pin it in place. We actively freeze out the decoherence. And what's so powerful about this is that it's not about fixing errors after they've already happened. No, it's about using the Zeno effect to stop the errors from ever happening to begin with.
But wait, it gets even more clever than that. We don't have to freeze the entire qubit solid. There's an advanced technique called quantum xenodynamics, and with this, we can design our measurements in such a smart way that they only freeze the bad stuff, the evolution out of the space we want to compute in. This creates this kind of protected bubble, a Zeno subspace, where the qubit is totally shielded from errors, but it's still free to do all the useful calculations we want it to do inside that bubble. It's like building a perfectly silent, completely error-proof room for our quantum computations to run in.
So let's wrap this up by looking at the really profound takeaway from this whole journey. Because the Zeno effect doesn't just give us a new tool, it completely rewrites our entire understanding of what observation even is, and what reality itself is.
Okay, first things first, let's bust a myth. This has absolutely nothing to do with a conscious person watching something. When physicists say measurement, they just mean any physical interaction that causes information to leak out from a quantum system into the wider environment. That's it. But here it is, the final, absolutely mind-bending twist. That whole watched pot analogy, it's completely backwards. Think about it. The reason a real pot of water in your kitchen doesn't exist in a bizarre quantum superposition of boiling and not boiling is because it's already being watched. It's being constantly measured by trillions upon trillions of air molecules and photons bouncing off of it every single nanosecond. All those tiny interactions are triggering a continuous, massive Zeno effect that freezes the pot into the solid, classical reality we experience. Our normal, everyday world exists because it's being constantly watched by everything else.
And that right there is the ultimate lesson of the Quantum Zeno Effect. It takes this old philosophical headache, the measurement problem, and turns it into a powerful engineering principle. It teaches us that in the wonderfully strange world of quantum mechanics, to observe isn't just a passive act of seeing what's already there. No, to observe is to interact, and to interact is to control. It gives us the power to actually shape reality at its most fundamental level.